So if I double the temperature, the peak wavelength only is half as big as it was before. If I triple the temperature, what happens to the peak wavelength? It's only what as big as it was before in that case. If I triple the temperature, lambda peak would be what times as big? Be bold. A third as big. You just flip it over. If I made the temperature, okay, I'm going to put you on the spot here. If I'm, oh my God,
Me?
yes you,
Okay.
yes you, oh my God, the camera's not turned towards you, so nobody will ever know. All right. So Jim, they'll never know. They'll think it's some guy named Jim. So
Okay.
Jim, if I made lambda peak 5 times, if I made the temperature 5 times bigger, what would happen to lambda peak? It would only be what?
1/5.
1/5! Jim, you're a genius. Way to go. Excellent. 1/5 as big. Yes. See, you rose to the challenge. It's okay. All right, you got it. Okay? Any questions? Okay, next topic. Something else you want to do? Yes.
Are we able to do, like, it's an example from the lecture tutorial?
Sure.
Okay.
Sure, throw something.
It's like when you're drawing, it's the light in atoms, so when you're
Mhm.
drawing it out, basically, it's which way it goes, and being able to tell what.
Yeah, so I think the way I would do that is why don't I bring up like one of those questions that I just, so, because that would be the way to talk about that. So, I gotta bring up the lecture tutorials. Light atoms. All right, and let's see. So, yeah, I'll just, before I showed the answer, but let's just do it again here, okay? So, of the atoms above, which one would be emitting light with the shortest wavelength? So first of all, is it the electron moving outward that corresponds to emitting light, or is it the electron moving inwards that corresponds to it emitting light? Inwards, because if it goes inwards, it's going from higher energy to lower energy. The electron is losing energy, and that energy is turned into the photon that it emits. So going inwards is emitting, going outwards is not emitting, instead it starts with an A, absorbing. That's absorption in that case. But here we're being asked emitting light with the shortest wavelength. So shortest wavelength, will that mean the least energy or the most energy? This you want to just be knee-jerk. For a photon, if I shorten the wavelength, do I make it more energy or less energy? Definitely more. So you just want to not even think about that. Shorter wavelength means higher energy. If you want to make it kind of intuitive, this isn't quite correct way to think of it, but still, if the wavelength is shorter, more of the wave crests are passing by you every second. So if you thought of them as punching you, right, you'd be being punched a lot more with the wavelength being shorter. So that must be more energy. You kind of think of it like that if you like. So, all right. So if it's going to emit light with the shortest wavelength, that says it has to be going down close to the nucleus. And so we need the biggest jump, because higher energy is a bigger jump, a bigger change in the electron's energy. So in other words, we can translate into which one, of all these four here, which one has the longest inwards pointing arrow, because that's what's representing that. The biggest inwards jump is the most energetic loss of energy by the electron, and thus emitting light with the shortest wavelength, highest energy. So A and C are the ones where the electron is dropping down, giving off energy. Which one is more energy being given off, A or C? C. So C. is the answer to that one. C must be the one where we have the emitting light with the shortest wavelength. What if I turned it into absorbing light with the shortest wavelength? Which one would it be then? Which ones are absorbing light? Is this absorbing light?
No.
Is this? Okay, we'll keep that one. How about this? How about that? Okay, so these are our choices. We want to absorb light with the shortest wavelength. So is that the bigger jump or the smaller jump? Bigger, because it's more energy. So who's the winner? D. So D would be absorbing light with the shortest wavelength. And if it was absorbing light with the longest wavelength, which one would be the winner? If it's absorbing light with the longest wavelength, B, yeah, because B and D are the choices because those are the ones that are absorbing, but longest wavelength would be the lowest energy, so B is the winner in that case. And so forth. That's how you reason through that. You got to figure out, okay, shortest wavelength, that means the most energy. I want the longest arrow. Absorbing, okay, I want an outward arrow. So what's the one with the longest outward pointing arrow? You just translate it like that. Which one is making the biggest jump outwards is what that would correspond to for absorbing light with the shortest wavelength, for example. Is it still recording?
Yeah.
Cool. It's probably on like the third file by now, but that doesn't. Okay, while you guys are thinking, I'm gonna go get my drink of water that I need right now. It turns into a game of chicken where everyone's like, I don't know, am I done? Nobody else is leaving. So then a few people start to leave, and then other people are like, should I leave too? I don't know, maybe someone's gonna ask this question. What was the question?
I already forget what you asked.
Did I ask a question?
I don't know.
I don't think I did.
Oh, okay. I thought you were waiting
Right.
for someone to answer something. But...
No, I was just gonna go get my drink of water.
Oh, okay.
Right. Yeah. How about this? Because if you could answer this question, seriously, you would win a Nobel Prize. Why does the fine structure constant have the value that it does? And why is it dimensionless? You're not going to be able to answer it because I can't answer it. I'd win a Nobel Prize if I could answer that question. Yeah, I'm just saying. You wanted me to ask the question, so I thought I'd ask a really good one. There actually is a case where a math professor was teaching a graduate student course, and he wrote a theorem on the board that nobody had ever proved. And one of the students came in late, and he thought that was a homework assignment, and so he did the homework, and he got famous because he actually proved this thing nobody had ever been able to prove before. So if he hadn't thought it was a homework problem, he probably wouldn't have even tried it. He would just assume nobody's figured this out, I can't figure it out. But because he thought it was a homework assignment, he actually figured it out. So.
You got mad at us for coming in late.
What's that?
You got mad at us for coming in late.
I did? What did I do that?
What?
Did I get mad at you for coming in late?
No.
Oh, okay, yeah. I mean, the professor was probably a little annoyed at him, but then then he gets what he thinks is a homework problem. He's like, no, this is not an assignment. It's like reading through, it's like, holy crap, you know. So, and it sounds like an urban legend. It sounds like one of those, yeah, yeah, sure, but you can look it up. It's actually true. You can look it up on the internet. That actually did happen. There's another story, this one probably is not true, where a professor would regularly show up late to class, and his signal to the students was to leave his hat on the desk. That was the signal that just wait for me, I will be coming soon. And it happened often enough that the students got tired of it, so one day the professor walks in and every place in the room is just a hat sitting on the table in front of the seats and nobody's there. That's good. It's probably not really true, but it would be good if it were true. More and more people are saying, nope, nobody's asking anything, I got nothing.
Yeah.
I don't know. Yes?
It's kind of the same relating to that, but it's asking about the colors for it.
Uh-huh, so you're talking about like the colors of the spectrum?
No, like, it's an example over there, and then like.
Oh, like, yeah, because you could also have something like for example, you could do something like, yeah, so read it out to me, let's just, okay.
Which shows the absorption of green light, and then it has a bunch of examples.
Right, yeah, and then, but it's also, it's probably got like 4 of them, right? Like, what are the
There's
colors
6 of
involved?
them.
What are the colors?
There's violet, blue, green, and orange.
Violet, blue, green, and orange. Okay, violet, blue, green, orange. See you later. Okay, so violet, blue, green, and orange. Okay, violet, blue, green, and orange. So these photons, which one has the highest energy? The violet does because it's got the shortest wavelength, right? So what has the next highest energy? And the next highest? And the next highest? Oh, that's convenient. They're already in order from highest energy to lowest energy. Okay. So if we just ignore the directions of the arrows here, we say we don't care whether it's emission or absorption. So if it's a given that one of these is for violet, one of them's for blue, one of them's for green, one of them's for orange, what has to be the violet one? What's your criterion? Relate that to the length of the arrow. The bigger the arrow, what's that say about the energy of the photon? The higher the energy. So, of all of those arrows, which one's the longest? Yeah, I would say D, right? Because that's all the way from here to that outer circle. C's good competition, but it's from that second circle to that inner circle. So not quite. So who's blue? Yep, C. Who's violet? D. What about orange? A, because that is the shortest arrow, the lowest energy. In other words, it's all about the bigger the arrow, the further it's jumping, the more its energy is changing. So you look at your colors and you put them in order of energy, either highest to lowest or lowest to highest, and you say, okay, the highest energy must be the longest arrow, and the next highest energy must be the second longest arrow, and the next highest energy must be the third highest arrow, longest arrow, and so forth. The other thing, though, is, if it's saying which one is absorbing green light, you got to double check to be sure that it's absorbing. So would absorbing be an outwards arrow or an inwards arrow? Outwards, because absorption is when you're eating the photon and using its energy to jump outwards. You're giving energy to the electron. So basically you got to pay attention to emitting. That means jumping down, closer to the nucleus. Absorbing, jumping up, farther from the nucleus. And you got to pay attention to the energy. The color tells you the energy, and so Like with this range right here, orange has to be the shortest arrow, lowest energy, violet has to be the longest arrow, highest energy. So that's how you can reason that out, is what it comes down to. Wow, we've been here that long already? Time flies when you're having fun. Now, whatever you do, don't be late. Figured I'd get that in there. Actually, what's bad is like, if one student doesn't show up for the exam, it's like, who is it? I can know everybody in the class, but it's really hard to figure out who's the missing person. If then they walk in, you're like, oh yeah, that's right, it's Murgatroyd. But until they walk in, you're like, wait, who's not here? It's really hard to figure out.
Dr.
Yeah.
Are you gonna announce like the assignments for Thursday at like in class?
Yeah, I'm not gonna give you anything for Thursday because that would be mean.
No quiz or
No quiz or anything.
Okay.
Yeah,
Or
you
even
just
a
have an
timed
exam. I want you to learn first and foremost, but I don't want you to hate me. So, it's just, it's not like, well, the perfect way to celebrate after an exam is to do a big homework assignment, so,
Thank you.
yeah. Yeah, remember there's quizzes up here.